All right, so next up is measuring pressure. So first we have barometer and manometer. So we need to know what those things are, and I have some pictures here to reference to for that. You don't necessarily need the pictures in your notes, but it's a good thing to work off of to start. So on the left here, I have the original barometer. Right? All Torricelli did was flip a test tube full of mercury in and then inverted it into a pool of mercury. And when he did that, because mercury is so heavy, it would pull down in the test tube to create a vacuum above that mercury in the test tube. Now, this system that he created, right, can help us measure that atmospheric pressure. So atmospheric pressure pushes on the surface of that mercury. So you can see that happening over here, right? Atmospheric pressure pushes down on the mercury in the pool, which actually causes the mercury to climb up the test tube, which gives us this measurement, 760 millimeters, which you should recognize because 760 millimeters mercury is 760 torr. Right, so that was our first pressure measurement, and that's equal to 1 atmosphere of pressure. So this barometer, it must be at sea level at 0 degrees Celsius. Otherwise, if it wasn't at sea level, if it wasn't at 0 degrees Celsius, that pressure reading would be different. So if you brought it up to our level, remember we're at 2,000 plus feet in our classroom, that pressure would be lower. The mercury wouldn't climb as high because our atmospheric pressure wouldn't push as hard on the pool of the mercury outside of the system. So again, literally we're measuring mercury in millimeters, and it gave us this unit torr. Otherwise, that's a barometer. Millimeters mercury, again, is the same thing as torr, so we use torr as that pressure unit. A manometer is slightly different. I'm still measuring pressure, but I'm actually comparing pressures. So if I have two different pressures, I can compare those pressures, and the difference in heights on one side and the other are going to give me a difference, a change in pressure. So I'm looking at these pictures again. First one here, option A, I have two pressures that are equivalent to each other. If I have some liquid in this tube, right, pressure 1 and pressure 2, if they're equivalent to each other, then that liquid should be at the same level on both sides. Right? In picture B, pressure 2 is different than pressure 1, right? Pressure 1 is pushing down harder on that liquid, causing the liquid to rise higher on the right than on the left. That means that pressure 1 is bigger than pressure 2, right, as it says below. Right? In the third situation, C, pressure 2 is bigger than pressure 1. Now, if that was mercury in those tubes, and I'm comparing two pressures, what I can end up doing is actually knowing one pressure, figure out what another one is. So the purpose of a manometer is I would have pressure 1 that might just be my atmospheric pressure that I can measure with a barometer, like the barometer on the left. So let's say atmospheric pressure is that 760 torr. And then I have a difference in pressures between 1 and 2, and I can literally measure a height difference from here to here. And as long as that's mercury in those tubes, the millimeters of mercury difference there give me a difference in pressure. So if I knew that that was 20 millimeters, that difference, then pressure 1 is 760 torr, but pressure 2 is obviously 740 torr, right? Because it has to be a smaller pressure than pressure 1, and the difference literally gives me the torr units. So as long as I measure that in millimeters, I can just subtract and get a new pressure for pressure 2. Whereas in situation C, if pressure 1 is still 760, then pressure 2 has to be bigger than 760, so I'm going to add to 760. So if I measured that difference and it was still a 20, pressure 2 in that situation is going to be 780 torr instead. So assuming that all of these pictures go together and that those pressure differences, that height difference in option B and C are 20 millimeters for both, and assuming that the liquid's mercury, I can know multiple pressures from those systems. I can infer the pressure of one from the other just by making that measurement, that difference in height. So I got barometers and manometers, right? If I have two different samples, I can know the pressure of both, right? If I know the pressure of one, I can figure out the pressure of the other, excuse me. A barometer gives me that atmospheric pressure, and that's what I'm typically comparing to. So pressure 1 was atmospheric pressure in each condition, A, B, C. Otherwise, our other connection with pressures is actually measuring blood pressure, because actually liquids can also exert a pressure on their surroundings. So when Torricelli was talking about an ocean of air, right, when you're at the bottom of the ocean, or if you're even at the bottom of a pool like the pool in Gordon, you can feel the pressure of all that liquid above you. So liquids exert pressure just like air does. So we can use that to our advantage. We can measure things like blood pressure. So we're going to talk about how that works. I might be able to do this in class. I'm not necessarily sure. If you guys remind me about it, you really want to do it, we can try. We can have the nurse come and show us how to measure this specifically. But we can talk about the theory of it and how it works. Right, so you have these two values in blood pressure, systolic, diastolic. Normal blood pressure is like a 120/80, right? So that doesn't mean that everyone really has to be a 120/80. It just means that's the average blood pressure for most people, right? So you may not have that average blood pressure, and you might still be healthy. It doesn't actually mean a whole lot right away. But people with high blood pressure, right? High blood pressure is associated with a lot of different health problems. So it's measured frequently in a hospital, and it's one of those stats that they keep track of to see how conditions for that patient are changing. So measuring blood pressure, you actually use a sphygmomanometer, which is a mouthful, but basically you have this bulb and a cuff, right? You use the bulb to fill the cuff with air and create a pressure big enough to cut off the circulation, right? To cut off the circulation, collapse that brachial artery in your arm, right? So once you do that, you're going to end up, right, with no blood flow, but you're going to put the stethoscope on that artery in your elbow, and you're just going to start listening, because once you have that blood flow cut off, you just release the pressure in the cuff. And as that cuff is deflating, right, its pressure continues to drop, and eventually the pressure in the cuff is going to dip below that systolic pressure. So systolic is the high end pressure. And once that systolic pressure is bigger than the cuff pressure, blood's going to start flowing again. But it's only actually going to be flowing, it's only going to be able to push its way through when the heart's contracting. That's when that systolic measurement is red. That's the high end, because the heart is contracting and pushing blood through your vessels, right? Whereas the low end of blood pressure is the diastolic pressure. That's measured when the heart is relaxed, when it's not contracted. So I have this systolic pressure. Once it's bigger than the pressure in the cuff, that's when I get to start hearing heartbeats again. So that's the first number you're going to write down. You're looking at a manometer, just like we talked about before, and that difference in height gives us a pressure that we can use. right? But then as more and more air escapes from the cuff, the pressure continues to drop, and eventually the cuff pressure is going to dip below even that diastolic pressure. So the pressure when the heart is not contracting is bigger than the cuff pressure. At that point, because the blood doesn't have to force its way through the cuff, you stop hearing heartbeats. So there's this little Goldilocks range where you can actually hear the heart beating when you put that stethoscope again on the brachial artery in your elbow. And you're just trying to figure out those 2 points, right? The high end is when you start hearing the heartbeat because the systolic pressure is just big enough to overpower the cuff pressure. And then the low end is when the blood doesn't really have to work to get through the cuff, right? You stop hearing the heartbeat once the cuff pressure is below the diastolic pressure. So you have 2 different pressures, one's higher, one's lower. And once you get those 2 readings, it gives you literally that 120, 120 over 80, maybe, if you're healthy, right? But again, you don't actually have to have a 120 over 80 to be healthy. Usually they would compare your normal to what's going on, right? So if all of a sudden it's 3, probably more like 180 over 110, that means that your system's a little bit out of whack, right? So we're going to do this blood pressure idea. We need to understand how that might work because that's the whole point of biochem. It's all focused towards medical fields. So it's something you might have to learn how to do because they do use machines in hospitals to actually measure blood pressure, but if there was no power, you would have to go right back to the old school way of doing it. And that happens every once in a while. Maybe not in the hospital itself with generators, but maybe in an ambulance, right? So you just got to do what you got to do.